Hessian equation in pseudo-Kähler.
Thank you. This is my fourth time at IMPA. The first one was in 1980. Back then it was, I think, in Rua Carioca. And it's always a great pleasure, and thank you for inviting me. What I'm going to talk about is split into two topics. The first one is a joint result, a couple of joint results with Ivo Terek, and it's about holomorphic vector fields on pseudo-Kähler manifolds. More precisely, the result says that if you have a pseudo-Kähler manifold, then and it's compact, then every killing field on it is necessarily holomorphic, provided that this underlying complex manifold has the DD bar property. In other words, as people say, satisfies the DD bar lemma. Let me elaborate on this. A pseudo-Kähler manifold, not surprising, is a pseudo-Riemannian manifold with a fixed almost complex structure which is orthogonal with respect to the metric, in other words, skew adjoint with respect to the metric, and parallel. And integrability of J follows. I'll comment on that in a moment. And the statement of the main theorem is that a killing field on a compact pseudo-Kähler manifold with the DD bar property is necessarily real holomorphic. And in complex dimension 2, the same assertion holds without assuming the DD bar property. So let me very quickly elaborate on some details here. First of all, if you write the Naehenhuis tensor of any almost complex structure using the formula on top, then obviously you can fix an torsion-free connection on your underlying manifold and rewrite this Naehenhuis formula in terms of the connection. And then you see very clearly if this connection makes J parallel and vanishes identical. In other words, you have integrability under an even weaker assumption that this is a so-called, that the manifold, almost complex manifold in question admits a so-called Kähler connection, a torsion-free connection making J parallel. Torsion-free is crucial because there will always be a connection making J parallel. J turns the Tm into a complex vector bundle, and any connection that complex vector bundle makes J parallel. J is the multiplication by I. So torsion-free is crucial. That guarantees integrability. Then I would like to very quickly mention, I'm going the wrong way, sorry. Mention two facts, namely, or three very, very easy, very trivial facts. First of all, if you have a differential form on a manifold which is closed, and any vector field V, theta is your form, then the Lie derivative of that form is exact, because the Lie derivative acting on differential forms is expressed through the Cartan homotopy formula. It's the anti-commutator of the interior multiplication by V and the exterior derivative. So LV of such a form produces D of something very explicit. Secondly, if you have a connection on a manifold and a vector field and any tensor field which is parallel, then I guess I did not write that assumption. The tensor field is assumed to be parallel instead of being preserved by the flow. Sorry, that's a typo. I'm assuming that the connection is preserved by the flow of the vector field. In other words, this is an affine vector field, and the tensor field theta is parallel relative to the connection, not preserved by the flow. It follows that the Lie derivative is parallel as well for very obvious reasons. You can either invoke the Leibniz rule here, or simply observe that the flow, preserving the connection, will push forward your tensor field onto a curve of parallel tensor fields. So when you differentiate that curve, you get your Lie derivative, and that's parallel, of course, again, because it's a derivative of curve of parallel tensors. So we have these two facts. And the third fact is also a very immediate. If you have an exact P form then it is, on a pseudo-Riemannian manifold, then it is L2 orthogonal to all compactly supported parallel tensor fields of the same type as this form, because when you take this tensor field and as we see in this, where did I have it? When you integrate by parts, when you integrate by parts, your form is exact, so it's D of something. You integrate that against your tensor field. You can replace the tensor field with skew-symmetric part because the other factor is skew-symmetric, and then you move D to the other factor using D star instead. However, since the other factor is parallel, D star annihilates it. So instead of parallel, you could assume just that the skew-symmetric part of your tensor field has divergence 0. And you get this orthogonality with respect to this possibly indefinite L2 inner product arising from the Fourier metric. So one special case of this is, of course, if your form is both exact and parallel, then it is L2 orthogonal to itself. And actually more follows. It's not only has the integral of its inner square, quote unquote, equal to 0. The inner square is identical to 0 because that inner square is constant since your form was exact and parallel to begin with. So in other words, an exact parallel form is necessarily pointwise null on any pseudo-Riemannian manifold and a compact pseudo-Riemannian manifold. Let's say compactness is, of course, needed here. So we have those elementary facts, and now I'm going to point out that theorem A, saying that on a compact pseudo-Riemannian manifold, a killing field is necessarily holomorphic, is well known and trivial in the Riemannian case, where the metric is positive definite. There are two separate reasons one can name. One reason is that if you look at the flow of your killing vector field, this is just the very bottom here. If you look at the flow of this vector field, the flow acts trivial in cohomology and pushes harmonic forms forward onto harmonic forms. And your omega, the Kähler form, is harmonic, and therefore it has to be preserved by the flow. LV omega is 0, and that implies it's the same as saying that LVJ is 0, which is holomorphicity. On the other hand, you can also derive it in the Riemannian case. By the way, at the top there is this argument about the L2 inner product, which I just stated in words. But here, you can also derive the same conclusion about the Riemannian case as follows. As I just mentioned, the lead derivative with respect to a killing field of the Kähler form is once exact, which is the case of the derivative, any lead derivative of any closed form, and secondly, it is parallel because the Kähler form is parallel and your vector field is a killing field. It's both parallel and exact, and you observe that such a thing, being parallel and exact, is necessarily, on a compact pseudo-manifold, is null. If your manifold is Riemannian, being null means being 0, and we get LV omega equal to 0 again. So being able to switch from null to equal to 0 seems to require positive definiteness of the metric. However, in complex dimension 2, this still follows even when the metric is indefinite for the following reason. So this is the proof of the theorem I named theorem B, which says that this conclusion about real holomorphicity of killing fields on compact pseudo-Kähler manifolds in real dimension 4, in complex dimension 2, does not require assuming the DD bar property about the underlying complex structure. Because what happens, if you take the lead derivative of the complex structure tensor, I keep hitting the wrong button, I'm sorry. If you take the lead derivative of the complex structure tensor with respect to a killing field, LVJ, that is equal to the commutator. The lead derivative is equal to the commutator of J and the covariant derivative of V. So I'm sorry. So the Lie derivative is equal to the commutator of your J complex structure tensor and the covariant derivative of V. The commutator is automatically anti-commutes with J. In other words, this Lie derivative as a 1-1 tensor field, as an endomorphism tangent bundle, is anti-linear. At the same time, because the covariant derivative of V is skew-adjoint, your V was a killing field, this is a skew-adjoint anti-linear endomorphism. In complex dimension 2 and real dimension 4, you are on an oriented pseudo-Riemannian manifold, which is, if it's indefinite, if the metric is indefinite, it must be of the neutral signature. So you still have the decomposition into lambda plus and lambda minus, self-dual and anti-self-dual forms. And being your skew-adjoint endomorphism corresponds to a differential 2 form. And the fact that this 2 form is anti-linear as an endomorphism means that it is self-dual and orthogonal to the Kähler form. And that means it lives in a complex line bundle. If you hit such a form, compose such an endomorphism with J from one side, you get another such endomorphism, which means this is a section of a complex line bundle in which your metric determinants is a real part of a Hermitian fiber metric. In complex dimension 1, metrics are positive or negative definite. So even if the original metric was indefinite, this section, which we discovered was null, lives in a bundle with a positive or negative definite metric, and therefore it is identically 0. So we have the proof of this fact in complex dimension 2. Now, let me move to the general case. So we are looking at I'm phrasing the D-bar lemma or D-bar property. If you have a complex manifold, assuming that it's compact and carries a Kähler metric, it satisfies the following condition, namely for any pair of non-negative integers p and q, if you have a closed PQ form, which is also partial exact or partial bar exact, then it is equal to d bar partial bar lambda for some p minus 1, q minus 1 for lambda. We really need only a special case of this to be applied directly, namely the case where q is equal to 0. Now, this still holds where the convention is, of course, that forms having a negative part in their degree are automatically equal to 0. So when you phrase it like that, if you have a compact complex manifold with a DD bar property, and you have a P0 form such that partial of this form happens to be closed, so this partial of the form is closed and it's also partial exact. And therefore, it is equal to partial bar of something which is necessarily 0 for degree reasons. So then this is 0. In other words, if your form is closed, if partial of a P0 form, the partial image of a P0 form is closed, it is necessarily equal to 0. Now, this takes us to the following observation. If you have a compact complex manifold with a DD bar property, there are no non-zero exact P0 forms. A P0 form which is exact must be equal to 0, and that's precisely what we saw on the previous page. You see, if you have this P0 form of which is exact, being exact means the same as being partial exact because there is nothing to contribute to the partial bar image. So this means you have a P0 is partial exact, which means this situation, your form is partial xi, and therefore being of type P0, it is necessarily 0. Again, on a compact complex DD bar manifold, there are no non-zero exact P0 forms. And that will take us directly to the proof of the theorem. But before I proceed there, I need to state this well-known fact of the Hodge decomposition in complex cohomology, which follows when the underlying compact complex manifold has the DD bar property. Actually, people prove that this is equivalent to the DD bar property. And this, the statement would be like this. You have the direct sum decomposition of the cohomology where each HPQ consists of cohomology classes containing closed PQ forms. So the crucial part here is the directness of this decomposition, that there are no intersections of partial sums of this against other partial sums. So in particular, we have the following consequence, that in a compact complex manifold having a DD-bar property, we have this displayed statement: a cohomology class is real if and only if for all P and Q, its HQP component is equal to the conjugate of its PQ component, because that's how the conjugation operates between those summands of the Hodge decomposition. So that will come very handy in a moment, because now we can prove this theorem A. So how do we proceed to prove it?
So you're in a situation where the Hodge-Duran spectral sequence degenerates. You might not have Hodge symmetry, so H.
Yes,
HQ
yes.
Might be different from HQ.
Yes.
But you can look at the case where.
Yes, and there's a neat direct sum decomposition. So reality means having the PQ and QP components which are each other's conjugates necessarily. Because now look what happens. I'm looking at this the DD-bar compact complex manifold with a pseudo-Kähler metric and a killing field. And I'm looking then at alpha, which is the Lie derivative with respect to that killing field of omega, of the Kähler form. I want to show that alpha is 0. So what do I know already? We observed alpha is parallel and alpha is exact. And alpha also corresponds via the metric to capital A, which is the commutator of J and this skew adjoint endomorphism, the covariant derivative of V, and therefore it is antilinear. And for A being antilinear means that alpha has this property here. Alpha pulled back by J becomes minus alpha. That means that alpha is the real part of a complex bilinear form. This complex bilinear form is written explicitly as the form zeta in lemma H. Zeta is alpha minus IA alpha J dot dot. This form is of type 2-0. In other words, complex bilinear. It is also necessarily holomorphic because it's parallel. But that turns out to be irrelevant for our purposes, this holomorphicity. The point is that in the case where M is compact and has the partial bar property, while alpha is exact, this alpha will be necessarily equal to 0, because we saw an exact P0 form is necessarily 0. So we need to show that this alpha is exact, that alpha is exact. How do we show this? So we are looking at our, let me go forward. We are looking at this observation. First of all, zeta is parallel. This form, zeta, let me remind you, was the complex bilinear form with a real part alpha. This is parallel because alpha is parallel, so this is holomorphic. Now, no, I'm going in the wrong direction. So it is holomorphic because I have the statement preceding lemma H. Let me point it out. If you have a closed P0 form, it is automatically holomorphic. Why? Being closed means you get 0 when you hit it with partial plus partial bar, but partial bar gives, partial on it gives 0 automatically for dimensional reasons, and therefore its partial bar image is equal to 0. So in this way, so more precisely, the partial bar and partial image of it live in different summands of the decomposition of differential forms, and therefore being declosed implies being partial closed and partial bar closed. So, and partial bar closed in this case makes it holomorphic. Makes it holomorphic because of the by degree being P0. So our form alpha being closed due to its parallelity is necessarily holomorphic. So now what we are looking at is this observation that so this form is holomorphic and exact y. Alpha is exact because it was the Lie derivative of a closed form. Now, because alpha is exact, if you look at the zeta, having the real part alpha, and if you multiply by I, you get your alpha, and due to, in other words, due to exactness, exactness of zeta makes I zeta a real form. Let me say it again. Our zeta is exact. If you multiply zeta by I, this has sorry, let me backtrack. What we know is the following, that we know that alpha is exact. That means if you multiply, if you look, alpha is exact. Therefore, the real part of zeta is exact, which means if you take I zeta, it is real. Its imaginary part is exact, trivial and cohomology. I zeta is real. However, I zeta is of type 2,0, and being real, it is equal to the conjugate of its 0,2 component, and the 0 component is 0. This is a form of type 2,0. And we conclude that this form is 0 from the reality criterion associated with the Hodge composition. And the theorem follows. We verified suddenly that this form alpha, the Lie derivative of the Kähler form with respect to our Killing field, is necessarily equal to 0 as a consequence of the partial bar, DD bar property. And this theorem is proved. So let me now move to the second part of this presentation. This is joint work with Paolo Piccione. And I mentioned the first part was joint with Ivo Terek. Now, we're talking about what's called special Ricci-Hessian equations on Riemannian manifolds. We are particularly interested in the case of Kähler manifolds. This time, the matrix will be positive definite. A special Ricci-Hessian equation is a condition of the following form. Alpha times the Hessian of tau plus the Ricci tensor equals a function sigma times g, where tau is some function on your manifold, on your Riemannian manifold. Alpha is assumed to be a function of the variable tau. Alpha is a function of tau, and alpha times the Hessian of tau plus the Ricci tensor equals a multiple of the metric. Why are these things of interest? The reason is they come up very, very naturally in a variety of interesting situations. Let me quickly mention those examples, but before I proceed further, I would like to emphasize that the focus here, my focus, is on the Kähler case. In the Kähler case, since I made an assumption here that I didn't phrase in words, but let me point out, I'm assuming that this term alpha times the Hessian of tau is non-zero almost everywhere. I don't want anything trivial to happen there. This is assumed throughout when we discuss such an equation. And that means in the Kähler case, if you look at both sides, you see R is Hermitian, G is Hermitian, therefore the Hessian of tau is Hermitian, and therefore tau has a holomorphic gradient. So in the Kähler case, instead of saying it like this, you can simply say that V, the gradient of tau, is holomorphic, and the one part of both sides is equal to 0, which means I alpha DD bar tau plus the Ricci form is equal to sigma times the Kähler form. So this is the Kähler case. Now, there are three natural cases in which such a situation occurs. Because we are already restricting this discussion to the Kähler case, this almost soliton option will not occur. And the almost soliton option in which you have the soliton equation with a constant times the metric instead of a function, in the Kähler case, it automatically forces the constant to be 0 because of closeness of the associated 1-1 forms. So we have a gradient Kähler-Ricci solitons. That's one class of examples. Secondly, conformally Einstein-Kähler matrix, or more generally, any conformally Einstein matrix, because then you have such an equation with alpha equal to that particular function of the variable tau, and the Einstein metric is this. In complex dimension 2, as Claude mentioned, tau may be assumed freely to be equal to the scalar curvature. You have to divide this Kähler metric by the square of its scalar curvature to get an Einstein metric, provided that the scalar curvature is not identical to 0. And finally, there are those objects called special Kähler-Ricci potentials on Kähler manifolds. Let me briefly mention the definition. It's an n non-constant function of your Kähler manifold which has a real homomorphic gradient, which at points where the gradient is non-zero, the vectors orthogonal to it in the complex sense, orthogonal to this gradient and its J image, are eigenvectors of both the Hessian of tau and the Ricci tensor. These objects have a heavy and strange definition, but that was justified by the naturality of this condition coming up in various circumstances. For instance, if you have a Kähler manifold with complex dimension greater than 2, its being conformally Einstein implies this. However, that does not happen in complex dimension 2, where very non-trivial situations occur, as discovered by Claude in that JAMS paper of 2007. So we are now returning to so there are these three classes of examples. So what I want to say is two of these classes, namely special Kähler-Ricci potentials, as I already said on the next page, they are completely understood. These special Kähler-Ricci potentials have an explicit local description and also an explicit classification of all the compact manifolds carrying such a thing. So they are of no interest to us. Let's leave them aside. Secondly, gradient Kähler-Ricci solitons. When I say gradient Kähler-Ricci solitons, on a compact manifold, you can skip the word gradient. It follows, as proved by Perelman. But anyway, gradient Kähler-Ricci solitons are widely, not completely, but understood to a large extent. So I would also like to skip them and look at what's left beyond them, beyond those two classes. So what is left beyond those two classes? First of all, let me introduce some notations. I will use throughout the following notations. V will stand for the gradient of our function. Q will be the norm squared of that gradient. Y will be the Laplacian of the function question, hence the real dimension involved. Then there are those two classes of functions studied and understood extensively, namely transnormal functions have this property. I'll use the following kind of abuse of language. When I say that psi is a function of tau, I'll mean that this is true locally at points where the gradient or the differential of tau is non-zero. And that means the same as saying that d psi wedge d tau is equal to 0. So we call a function transnormal if the norm square of its gradient is a function of tau in this sense, and that amounts to saying the same as that the integral curves of the gradient are reparameterized geodesics. So that's the class of transnormal functions, and an isoparametric function is one which is both transnormal and also has the Laplacian, which is a function of tau itself. So these functions, transnormal solutions of our special Ricci-Hessian equation happen naturally in a variety of situations. First of all, I'm phrasing this using the harmonic flow property, but I'll skip that concept here. I will simply say, in the Kähler case, this assumption is satisfied. In the Kähler case, where you have a real dimension different than 4, and you have a special Ricci-Hessian equation, it follows that tau is transnormal. Actually, more follows. It's also isoparametric. And so the function on the right-hand side is a function of tau. At points where alpha and alpha prime are not equal to 0. Alpha was assumed not equal to 0 almost ever. Alpha prime not equal to 0 means we are excluding Kähler-Ricci solitons. In the non-Ricci soliton case, this equation dimensions other than real dimensions other than 4, transnormality follows, and that's one case where we get transnormality. There's another case where we get transnormality. Namely, imagine that alpha double prime plus alpha alpha prime is different from 0. This alpha is a function of the real variable tau. Assume it's different from 0. I'm taking points at which this time the differential of tau is different from 0. And at those points, in the Kähler case, the solution is again necessarily transnormal, actually even isoparametric. Why do these two conditions follow? Let me very, very briefly mention that. Namely, you get a bunch of conclusions. In the Kähler case, if you have such an equation, there are 4 functions. They are built from the norm squared of the gradient and the Laplacian of your function tau. There are these 4 functions which are necessarily functions of tau. How do you get such conclusions? You hit your equation with the 3 most obvious first-order differential operators. The trace followed by D, the divergence, and the third one is not differential. It's just an evaluation on the gradient V, the interior multiplication by the gradient. And that gives you further conclusions where you use the Bochner formula where the Ricci tensor is engaged against V, because that will give us the differential, -1/2 times the differential of the Laplacian of your function. In any case, you get a bunch of bunch of equalities between 1 forms, and if you gather them, if you look at them, gather them correctly, you will see that certain expressions have differentials which are function multiples of d tau. There are these 4 functions which are whose differentials are function multiples of d tau. In other words, they are functions of tau in this weak sense that I mentioned before. And for instance, if you look at the expression here, where there's n-2 next to sigma, and this one, where it's 2 next to sigma, if n is different from 4, it follows that q and sigma are both functions of tau, trivially. So that's how you, if you look at the other 2 equations, this one here, the first one and the fourth one, in place, if you equate both to a function, to functions of tau, you get a system of linear equations, and this alpha, this expression, alpha double prime plus alpha prime, is the determinant of that system. So if the determinant is non-zero, your q and y become functions of tau again. Therefore, you have to, in this situation, you get transnormality. So transnormality occurs again when you have that equation and when n is different from 4, and we don't want transnormality. Here is why we don't want it. Because in the Kähler case of such an equation, let's consider an open subset in which alpha and alpha prime are different from 0. In other words, I'm excluding the Kähler-Ricci-Soliton case, and then each of those conditions, the dimension being greater than 4, real dimension, or transnormality, on this open set, they both imply that we're dealing with a special Kähler-Ricci potential. And these things are completely understood. These are the things we want to exclude. So therefore, we exclude the dimensions different from 4, and we don't want transnormality, and because we don't want transnormality, that means we want alpha double prime plus alpha alpha prime equal to 0, and we also want the dimension to be equal to 4, the real dimension equal to 4. So this is where we are now. We are looking at this situation where I'm assuming that we have this special Ricci-Hessian equation holding on a Kähler surface. Now, I already reduced this discussion to the case of real dimension 4. There is a Kähler surface. I'm assuming that we don't have transnormality, so dq wedge d tau is somewhere, everywhere in some open connected set. And then, as I pointed out, this equation here follows. And this equation can be, of course, rewritten like that. That's equivalent to saying that this is equal to a constant. The 2 alpha prime plus alpha squared is equal to a constant. And for these functions I just introduced with generic notations q and v and y, there are further conclusions. Some expressions built from q and y are constant, and there are 2 such expressions. And finally, this function alpha of the variable tau, if you divide it by 2 for simplicity, must be really one of 5 possible types. What are these 5 possible types? I say here up to affine modifications, so I need to mention what these affine modifications are. What do affine modifications mean? If you have such a special Ricci-Hessian equation, in the function tau you can perform an affine substitution. Replace it with an affine function of tau, and of course the equation will still hold once you apply a correcting constant factor in front of alpha. That means your equation will still be satisfied if tau is replaced by something like this, where c is a non-zero constant, p is a constant, and then alpha as a function of tau has to be replaced with alpha hat as a function of tau hat, given by this formula. So we are free to modify these functions, and therefore, of all the solutions of your equation, alpha double prime plus alpha alpha prime equal to 0, there are only 5 types left, 5 equivalence classes of these affine equivalence under such affine modifications. I'm excluding a 0 solution. It's of no interest to us. But in our discussion, even though the whole premise was that we are dropping conformally, we are dropping the case of Ricci solitons, and we almost completely drop the case of conformally Einstein metrics, at least in dimensions higher than 4. We don't want these cases dropped because the whole discussion becomes more natural if you allow them. We are not excluding them. We are excluding transnormality, but allowing the case of a Ricci soliton in complex dimension 2 or a conformally Einstein metric, which is actually present very non-trivially on compact manifolds in complex dimension 2. So let's take a look now at what happens. We get this conclusion in the theorem that your function alpha, if you divide it by 2, is one of those 5 cases listed in the bottom line. Up to affine modifications, these are the solutions. Then, what else do we see? Our square of the gradient, q, and the Laplacian, y, satisfy 2 conditions to say that 2 more expressions are constants. What are these constants in interesting cases? In the conformally Einstein case, what are these constants? One is the scalar curvature of the conformally related Einstein metric. The other is a constant that says that you're in real dimension 4. Your tau has to be really a multiple of the scalar curvature. That's the ratio between tau and the scalar curvature. So these are the constants. What are these constants in the soliton case? One is the soliton constant. Sigma becomes a constant. The other one is a constant that was discovered by Ben Chow a long time ago. If you have a gradient Ricci soliton, and then you take the Laplacian of that soliton function minus this gradient squared plus 2 times the soliton constant times the function, that's a constant again. So this is a well-known constant appearing in that case. So we have those 2 extra constants, and we have 5 types. Now, let me point out that if you look at this equation, alpha double prime alpha prime equal to 0, you can think of it as a vector field in the plane. If you introduce beta, which is the derivative of alpha, this is your equation. The fact that this epsilon appears as an integral of your equation means that the solutions really look like that. So you take this parabola, given by beta equal to -1/2 alpha squared, and shift it vertically by all possible distances. So we get this bunch of parabolas. However, on the alpha axis, when beta is equal to 0, you see your vector field has zeros there. This is a line of zeros, and therefore the actual integral curves are not the parabolas, but what you get when you cut those parabolas using the alpha axis. So I'm marking it by empty dots here. So this is an integral curve, that's an integral curve, here's an integral curve, here's another, this is a full parabola, which is an integral curve. And again, each of those points constitutes an integral curve. So now the 5 cases, as I marked here, are like this. Here, each of those points represents the class of the solution 1. This is the solution 1 over tau, or that's another copy of it. They are equivalent under such an affine modification. This is the cotangent of tau. This is the hyperbolic cotangent up to here or there, and that's the hyperbolic tangent. So we have all those integral curves representing such solutions. Now, let me point out what becomes very interesting here. 2 special cases of this situation have been studied and are well understood. One was the discovery by Claude and co-workers that the 2-point blow-up of CP2 admits a conformally Einstein-Kähler metric, which is actually unique up to rescaling and pushing forward by the automorphisms from the identity component of the complex automorphism group. So that's the Chen-Lebrun-Weber metric on the 2-point blow-up of CP2. And on the same manifold, there's another interesting and distinguished metric, the gradient Ricci soliton, which exists according to a much more general theorem due to Wang and Zhu, who proved the existence of solid Ricci soliton metrics on all toric manifolds, admitting Kähler metrics. So both of these metrics have the maximum symmetry. In other words, they are toric. The conformally Einstein one because of being an extreme of Kähler metric, the other because Ricci solitons are automatically automatically have the highest degree of symmetry. They're an isometric group. A connected isometric group is the maximal compact subgroup of the automorphism group. Anyway, we have those two metrics on that compact manifold, quite non-trivial topologically. The metrics were found using very sophisticated arguments. They're not explicitly known. And the question is there a connection between them? How can we relate those two metrics to it? There are two distinguished metrics on the same manifold. How do you connect them? This picture could possibly offer such a connection. I don't know if it does. But here's a finite dimensional family of equations, not metrics. I don't know about the metrics, but the equations form a finite dimensional family. So, for instance, you could look at this soliton here and this conformally Einstein metric there and think about connecting path through intermediate solutions. That would be the hyperbolic tangent type solutions would be intermediate. Let me point out that it seems that if you find such a path, it would be continuous but not differentiable. Because if you try to deform those functions to get from some solutions to others of a different type, there are analytic continuation phenomena. I mark them in green. There's one analytic continuation process that goes this way. You can deform this function and analytically, so it becomes this on one side and that on the other side of the deformation. Also, you can take a constant, deform it analytically, so it becomes the hyperbolic tangent on one side and hyperbolic cotangent on the other side. So this is the natural way of going smoothly, I mean, analytically in this case. So such a connection would possibly be non-differentiable. But anyway, this is something that's worth trying, I believe. And I would like to now proceed to point out that even though we don't know if these equations, other than the special case I just mentioned, the case where alpha is a constant, non-zero constant, that's a Kähler-Ricci-Soliton case, and the conformally Einstein case, these are realized on compact manifolds. They're also realized on the one-point blow-up of CP2 in a much less interesting way. The conformally Einstein case is a Calabi metric conformal to the Page metric, and the soliton is the four-dimensional case of the Koiso-Cao Ricci-Soliton. But the point is that we don't know if such metrics having a different style of this function alpha, different from this and that style, if they exist on compact manifolds. However, what we can do is prove there are non-compact examples. And of course, instead of saying that each of those remaining three types, outside of these two there are three types, you can equally say that every alpha is realized. It doesn't make any difference because of those affine modifications. So it's simpler to consider alpha generally a single alpha instead of looking at three separate cases. Everything works out in the same way. And the argument even catches those cases that are already known, although we don't know. We don't need to address that at all. So now there is this theorem 6 I announced here. So the theorem says exactly that each of those options is realized by a special Ricci-Hessian equation on a real analytic Kähler surface of real dimension 4, such that with V denoting the gradient of tau and Q the norm squared of that, one has the non-transnormal situation, and in addition, there's an extra symmetry. You see, V is a holomorphic gradient, so JV is a killing field. We want another killing field, linear independent from it. That is suggested by the compact examples. I don't know, they have toric symmetry. So we have this we want this local version of the toric symmetry. Instead of saying that there are two commuting killing fields, independent killing fields, I can say we have two commuting real holomorphic gradients. So in addition to this V, there will be another one. And I already stated that in the case where you have those solutions here, compact examples are known due to these classical existence theorems. So now we're going to establish the existence of local solutions. How do we do that? So first of all, we are restricting the situation to a so-called slice. You see, once you have this toric action, or a local version of it, the orthogonal complements of the orbits automatically at generic points form an integrable distribution with totally geodesic leaves. And the metric, once you know it on such a slice, on such a leaf, is uniquely determined everywhere because those leaves are mutually isometric. So we are really discussing a metric on a surface. So I'm choosing those two holomorphic vector fields. One is our V, the gradient of tau. I'm adding another holomorphic gradient, linearly independent from it. So locally, wherever they are linearly independent, they are the coordinate vector fields for two real coordinates, x and u, on your slice. Actually, those coordinates on your slice form the real parts of a complex holomorphic coordinate system like this in a neighborhood of a given generic point on your manifold. And now I'm introducing what? The matrix of the metric restricted to the slice. So I'm taking, in other words, G of VV and so on. This is the Gram matrix, which is the matrix of the components of the metric on your surface slice surface. And I'm denoting these functions by Q, S, and B. Q is already, of course, what it was before. And it's very convenient to introduce a fifth function, which will be S, present there, times our alpha, which is present in the picture all the time, minus the Laplacian of this function lambda, whose holomorphic gradient we added to the picture. So we have these four functions. M now stands for a neighborhood of a generic point instead of the original manifold. We are looking at it locally, and we want to discuss the situation in terms of these functions. Now, it turns out that everything becomes nicer if you introduce a symbol f for a certain function of a variable tau, which is built from alpha and the constants that our situation generates. So it's a nasty definition, but once you have this f in the picture, things become simpler. The point is that then there is a condition QB greater than S squared, which simply means that the matrix representing the metric has a positive determinant, and that condition tells you that if you look at tau and lambda, those two functions of holomorphic gradients, they form local coordinate systems. The transition from xu to tau lambda has a positive determinant, in other words. So I'm replacing x and u, these real parts of holomorphic coordinates, with tau and lambda. Those are two functions of holomorphic gradients that now serve as new coordinates on this slice. And in terms of this, our system, our question, what we're looking for, this equation we're trying to realize, becomes the following. It becomes a system first consisting of these 6 quasi-linear first-order partial differential equations. And there are some conditions. One says that the determinant of the metric is positive. And of course, Q would be, because of that, either positive or negative. We want it positive. That's the norm squared of the gradient. And we want Q sub lambda different from 0 somewhere y. We don't want Q to be a function of tau alone because that means transnormality. We're excluding transnormality, but we're allowing the case of a Kähler-Ricci soliton or a conformally Einstein case. Simply because the discussion would be just less elegant if we excluded those cases artificially. So now we are looking at this, and what can we say? Now, in order to establish the existence of solutions, the most obvious, the most natural and useful thing is to resort to exterior differential systems. So an exterior differential system, I have the definition here, it's any D-closed ideal in the algebra of differential forms on a given manifold. We have the concept of integral manifolds and integral elements, which means things that are potentially tangent space of integral manifolds. We'll talk about integral curves or surfaces and integral lines or planes. And let me proceed further. So we have to associate such a system, exterior differential system, with our equation in the following way, with that whenever you have a solution, and this solution will be a quadrupole functions, Q, S, B, G, of the variables tau and lambda, as it's stated here. Whenever you have such a solution, you look at the graph surface of that in the 6-dimensional space with the variables tau, lambda, Q, S, B, G. Then whenever this equation is satisfied, these differential forms you're looking at should vanish on the tangent plane of such a solution, such a graph surface of a solution. Now, because it's a graph surface, d tau wedge d lambda is non-zero restricted to this surface, which means we are free to multiply each of those equations by d tau wedge d lambda, and suddenly they become equations involving not partial derivatives, but just exterior derivatives. This is what Elie Cartan invented. Get rid of partial derivatives in favor of exterior derivatives. So in other words, I multiply, for instance, this is stated here, right, very obvious way. If I take a term phi z sub t, z is one of those four functions, or phi z sub lambda, that becomes, when you multiply by d tau wedge d lambda, this becomes phi dz wedge d lambda, or minus phi dz wedge dt. Or it's a phi without any partial derivatives next to it, it becomes this. So suddenly you have a bunch of several, as many forms as there are equations. You have 6 equations, you get 6 differential forms, and you generate a declosed ideal by those forms. And something can happen here, because there are only 2 forms present there, and this is not quite right, because what happens is that occasionally, among those forms you generated, there could be your system would contain theta wedge d tau and theta wedge d lambda for some one form theta. And then on every graph of a solution surface, on every integral plane, theta will vanish as well. Because if this product vanishes and that vanishes, if those 2 things vanish on a surface, then theta vanishes. So we are suddenly free to add some one forms to this system. In other words, a system of partial differential equations, a quasi-linear one like ours, does not uniquely determine an exterior differential system associated with it. There are many different, you can imagine many different exterior differential systems which still have the property that they vanish on all potential solution graphs. So what happens? We add to this system first one differential form which is this here, because it has this property, and the second one, which is less obvious, but this. Now we have 2 linear independent one forms present in our exterior differential systems. And in addition, there are a few, I lost count, several 2 forms, and they together generate this exterior differential system. So what can we say? You see, there is this concept of the space H. No, sorry. Yes, if you have an exterior differential system and you pick some p-dimensional integral element of this system, you look at the space H of E of all vectors that can be adjoint to your given subspace tangent space, so the span is still an integral element, so that all those forms from a system still vanish on that span. Therefore, if you look at our system that was built here, it turns out to have a very nice property. Namely, we are interested in integral elements of dimensions 0 and 1. Why? Because we'll be looking at extending them into a higher dimension. Those of dimension 1 will be extended to those of dimension 2. From curves, we'll generate surfaces, and we need surfaces as graphs of those solutions. So if you look at E sub p, which is of dimension p, and look at the space H of EP, they all have the same dimension, k of p, depending just on p. Namely, k of 0 is 4, and k of 1 is equal to 2. Namely, every 0-dimensional integral element has a 4-dimensional extension, which means there's a 4-dimensional space such that all the lines in that space are integral lines. Why? This is the simultaneous kernel of those 2 differential one forms we added to the system. And if you look at an integral line, then it's contained a horizontal, let me say everything is horizontal. Horizontal integral lines contain a unique horizontal integral plane, and that takes some matrix calculus. Some matrix turns out to have the right rank, and again, having this extra one form included is crucial here. These 2 dimensions are universal in our exterior differential system, which lives in an open subset of R6. This is what makes the argument work. What we are invoking here is called the classic result called the Cartan-Kähler theorem. It applies to real analytic exterior differential systems. Ours is definitely real analytic. Those functions are extremely nice. And It says something like this. Let me point out that I will be citing here in the original paper, we are citing this beautiful monograph, Exterior Differential Systems by Brian, Chern, Gardner, Goldschmidt, and Griffiths. So we are looking at, yes. So let me just backtrack one page. See, what happens here is that in order to apply this Cartan-Kähler theorem, we have some conditions that are somehow parallel to having a constant rank in more primitive situations. Namely, in addition to constancy of those dimensions I just mentioned, to constancy of the dimension of the space h of the for the integral elements that are of interest to us, we need to know about some codimension, namely, and these numbers are wrong. Not 8 minus 4 equal to 4, 6 minus 2 equal to 4 is the correct expression. Not 15 minus 11 equal to 4, but 11, what am I doing here? Not 15 minus 11, but 13 minus 9 equal to 4. Yes. Okay. Yes. 13 minus 9 equal to 4. Let me correct it once more. Equal to 4. Certain codimensions have to agree with certain codimensions. In other words, some submanifolds have to sit in larger manifolds in a correctly transversal way, and these conditions are satisfied very trivially in our situation, and that allows us to apply the Cartan-Kähler theorem. What does the theorem do? First of all, you're looking for integral curves, and that's not a big deal because you have the simultaneous kernel of those two one-forms, so this simultaneous kernel forms a four-dimensional vector bundle, vector bundle dimension 4 over your six-dimensional space, and you are looking in it. You are looking at all possible one-dimensional vector subbundles, and each of them is spanned by a vector field, and you are taking just integral curves of such a vector field. You generate integral curves of your system at will, horizontal integral curves. Once you have such a horizontal integral curve, the Cartan-Kähler theorem says that because of the constancy of those dimensions involved, there are four specific dimensions that agree between different points. You can extend such a curve locally, in a locally unique fashion, real analytically, to an integral surface. One crucial part of this is, of course, once you have such a curve, the candidates for the tangent planes of that surface are uniquely determined. Every integral line, horizontal integral line, sits in a unique horizontal integral plane. That's crucial here, but the rest of it also works, and the main step in that is, I think, the Cauchy-Kovalevskaya theorem about analytic differential equations. And I guess I need to stop here. Thank you.